So let's start. So good to see you in person. So today is going to be our second lecture of programming languages. First lecture was remote. Glad to see such a nice turnout or such a nice view count. So we saw in the first lecture we talked about the architecture, some different approaches to programming. And today we will talk about the history. We'll go through like the major major and not so major languages, like in a big kind of sort of like timeline of all the languages and actually what led to the languages, maybe some earlier history as well, right? So then also we'll get to the actual languages and actually some of the technologies we need in the following weeks. So today will be relatively easy, I think. It's just so we can relax, right? But maybe pay attention a little bit, right? So again, I will be using a notebook, but the notebook format will not be. I will not be able to use notebooks for everything, actually. And I see here the Ishango bone, right? So this is a notebook here, history notebook, right? So we'll go way back. Let's go down to 20,000 BC, right? And let me get a new link here, new hyperlink. Let me sign in actually first, so I can see. So I can actually maybe run some code. I don't think I'll have any code today, but maybe just in case. Yeah, okay, all right. So we'll make a connection. Okay. Okay, looks like, yeah, so Ishango bone is something like this. I don't know if you've seen this before. Looks like this, basically, right? So what's on there? Any guess? What's there basically? Any guesses?
Something.
To me?
It was used to count something.
Yeah, I mean, your guess is actually, I think, is just as good as any, right? Well, of course, some anthropologists, of course, they've done some more research, right? But actually, what this bone was used for exactly is not, is still open for the debate, right? As they were not doing any advanced mathematics, probably most likely 2000 BC, but they were counting things, right? So something. There's some theories. Maybe it was some moon phase, something like that. Some astronomy, astrology, right? But certainly they were counting probably some hunts, right? But anyways, it's a first early counting system, right? So I guess I'll use this link from Wikipedia. I'll do a hot link for this one, right? There we go. Hopefully Wikipedia does not mind. These guys apparently don't have a link anymore. Let's see. Yeah, there we go. All right. Now, so basically some large animal, and of course some counting. Maybe, well, again, so that's the question. Where are they actually doing any advanced math, right? So maybe some sequences, right? Come on, I want to close this. Right, so pretty significant, right? So it's not a programming language, obviously, right? So now we got this device, Abacus, right? So who has used this device? Anyone? Oh, wow! So tell me.
I even know how to count them.
Super. Do you have like an older relative who used this in a?
Yeah, my mother taught me when I was little, but I forgot how to.
Wow. Because again, the thing is, there have been some competitions, like people who are really experienced, like your grandmother or maybe somebody else from the older days. They could beat some regular calculators, actually, right? People who are really good with this device, with the Abacus, they're pretty fast for simple arithmetic, right? There's a carry, right? I know also for just very basics, of course. I don't really know how to do it well, right? Didn't have anybody teach me. Yes. So.
I mean, basically, if you enter the first value, because like second line from the top, it's
this one?
From 1 to 10.
Yeah.
Second one, it's from 10 to 100, like
yeah.
10, 20, 30. After the 1,000, 10,000, blah blah.
Mm-hmm.
And you add in like number by number. Actually, you're doing like calculating in the paper, but.
Exactly. So yeah, it is a rudimentary, but it still was very effective up to like 1980s in Soviet Union, right? Device, and I suppose it might be used somewhere else. Supposedly in China or somewhere else you can find it. I mean, somewhere else still in use. And nothing wrong if it works, right? For basic things, right? Why break it, right? So rows, column, beads are numbers, right? So so that those are sort of like, of course, early computing devices, right? And of course, we have computing device, and we also start getting into algorithms, right? Euclidean algorithm, again, or algorithm course. You guys, I think we didn't really talk about Euclidean algorithm, right? But one of the earliest ones, right? Which is for finding the greatest common divisor, right? And it's very simple algorithm, right? You have two numbers, right? You guys already know probably this way now. Remember it, right? And find the remainder, right? Modulus, right? And if it's 0, then B is the GCD, right? It's very simple 3-line algorithm, right? So pseudocode, right? But easy to transfer to Python or anywhere else, right? So we have a couple other algorithms like Babylonian square root algorithm, right? So pretty good one. There's Chinese remainder algorithm. Again, we'll not go into algorithm today, but just some of the earlier examples, right? But right, and of course sorting and things like that. So then we get to before we get to medieval age, we get to Antikythera mechanism. I think I showed you this before as well, right? You've seen this one, right? Or not? Not in this course. Not in this course, right? So okay, so if you didn't see the link, right? So where is this from? Which country?
Rome, ancient Rome.
Kind of, okay. I guess you could make an argument it's from ancient Rome, but not technically, a little bit more precisely.
France.
No.
Precisely.
Well, okay, well. So I mean, it's like the answer. Okay. What does it say? If you have a question about literature, you say Shakespeare or something like that, or you have a text, you say A. So what's the answer for ancient philosophy and things like that? Greece, of course, Greece, right? Yes, Greece, right? It's hard to go wrong with Greece, right? So, right, or you can say China, right? I've had some guesses, right? China, France, but yeah. So, because you see the olive, like you can see some. It looks Mediterranean, right? So yeah, but so it's actually circa 150 to 100 BC, right? So your answer Rome would be kind of correct, right? Because I think Greece was already under control of, I don't know, right? I think was it? I think Greece, because of course Romans were big fans of Greece actually, right? They sort of like all the gods and everything, like they were taking it from the Greek mythology, all the tech, all the early technology, right? Rome was a big admirer of Greek technology, right? So what is this device? So it was found under seas, right? It consists of, I believe, 40 some little wheels, right? So okay, so what did it do? Any guesses? What could it do? What can it do?
Predict astronomical positions and the
Yes, you can read it. Yes, very good. Yes, but again, that's the thing is with these things, unless you have unless you have a user manual for this thing, right? You don't really know for sure, right? It's one of the multiple hypotheses actually, right? We don't have literature on this as far as direct literature, right? But there is also, I should probably say, possibly, right? Other suggested uses would possibly be, arithmetic, right? Which I think is the most likely for sure, right? Maybe Olympic, predictions, among others, right? So this is not a, 100% sure thing, right? But a question again to you is this actually the device, right? Is this the device?
It's a recreation.
It's a recreation, of course, right? It was sitting 2,000 years in a sea, right? I don't know how it actually survived. Actually, I think there was the metal they were using. It was kind of not rusting. So the wheels were there basically, right? So, but yeah, you can certainly do arithmetics. So this leads to Blaise Pascal's calculator, right? And you know Pascal for sure now, right? Yeah. Some of you haven't programmed Pascal. Who has programmed Pascal? No one, right? Yes, a little bit.
We studied in school.
Okay, yeah. still use the Pascal, yeah. So, okay, this used to be like before Python took over, Pascal was the language to use for school, for basically for teaching, basically. And in fact, it's interesting, we'll talk about Pascal, the language, a little later on. Is there still some languages which sort of derive from Pascal? It's still kind of popular, actually, right? So Delphi actually is one of the technologies. Lots of people made apps in 90s using Pascal, actually. But okay, but let's go back to Pascal. Who blazed Pascal? Who was he?
Smart guy.
Smart guy. He is one of those polymath guys, right? He did everything, right? You heard of Pascal's wager? Do you know what Pascal's wager is? Right? Philosophical question. So if you think, okay, is there God or no God, right? It's better to choose the God version because there's no risk, basically. It's of course, you could talk about in philosophy whether this is actually a good argument, but kind of interesting. So he's also one of the guys who came up with the first methods of doing probability statistics. Probability mostly, gambling. People came to him with gambling problems, right? And he solved them, right? Again, one of the, like I said, he did pretty much everything, but he died pretty young, at around age 40. But yeah, so this Pascal's calculator, let me get a link for this actually, because we don't see it here. This is Leibniz, but let's go to Pascal. So let's get Pascal's. Pascaline, I think it's called Pascaline, I believe, right? Yeah, that's it. Pascal's calculator, I guess we'll go with Wikipedia, why not? Right, so he even got a patent, a royal patent in those days. That's a pretty big deal, right? So, because I think his father was doing taxes. He was doing taxes, right? And you could do addition and subtractions with this machine directly, and you could do, of course, multiplication and division through, by simulating this, right? So, again, Abacus still has, you can think of it, well, there's a relation between Abacus and this, right, of course, because you have the carry mechanism, right? You have to carry digits, right? So, this is mechanical process, right? You add some numbers, you enter some numbers, and you spin the wheel, right? So, pretty cool, right? His innovation made each digit independent of the state of the others, right? So you can simply cascade, right? So 50 prototypes. I don't know how much money he made on this, I wonder. Maybe one of you wants to do a report on this, how successful was this machine, right? But this was really influential, right? So his calculator was really influential. So let me, since it's so influential, I'll add a picture of it. Yeah, why not? Let's do it at home. An alt text, Pascaline. All right, so is it here? Yep, there we go. Right, so Leibniz, I believe, yes. Who is Leibniz? Anyone? Also a smart guy, right? Also one of those kind of pretty much polymath, right? So what is he? Well, okay, what is we could say? Okay, he has many things. He of course philosophy. Of course, in those days, everybody did philosophy, right? But math-wise, what is he sort of famous?
He had some discrete math theorem or something.
Yeah, not only that, but basically, you guys have taken calculus, right? Right. So the notation we use is actually Leibniz. There is a big sort of a fight or drama between Newton and Leibniz, right? They both came up with calculus sort of independently, right? But so Newton sort of claimed to be first, right? Leibniz was sort of a little bit after, but actually Leibniz notation was a little bit simpler to use, right? And actually we use that today, basically. I think the integral symbol, I believe, is his, I don't want to get wrong, but I think most of the early the notation we still use today is from Leibniz, actually, right? He had many big ideas, right? So, but his step to the corner, well, again, you can see the big spinners, right? Again, you can see how it works, right? And then, of course, we get to Charles Babbage, right? Charles Babbage, analytical engine, right? So this would be the first, there's analytical engine, right? And there's also difference engine. Analytical engine, basically, it's a mechanical general purpose calculator, right? So there is actually arithmetic logic unit, ALU, right? So, and of course, he also did difference engine, which was trying to be even more universal. You could think it's the first computer, actually, right? Mechanical. But no, there's no electronics those days, right? So this actually, he was basically a first computer, as we would understand it, right? But if you didn't have any electricity, right, you just had mechanical turns, we could run actually user programs, right? So we'll get to how do you write programs for that, those kind of things. What do you use for those? I mean, in those days, what do you think they would? What was the proposal? How would you enter a program in this type of machine? Remember, this is 19th century, 1837.
With strips of paper?
Yeah, basically yes, with punches, right?
Yeah.
Yeah. Do you guys know where it came from? This idea of punches. That was before that, like a couple of years, like maybe 20, 30 years before that, actually.
From like weaving machine?
Yes,
Yeah.
very good, right, excellent. Yes, it came from the weaving machine. So that's like, again, so all these steps together, right? There's a weaving machine before that, the storage, right? So the punch, the holes technology, which is actually with us till I think in Soviet Union, it was us is like 1980s actually, right? So maybe some banks still use somewhere, even in America, maybe some banks still use this punch hole technology, right, for storing. Like some shops from like, I don't know, 1950s, right? They still sometimes somewhere use this, right? I have never actually used them myself to write programs, thank God, right? Or thank I don't know who, but I have heard stories, right? So what you did in those days, well, in 1960s, 1970s, you punch the holes, right? You write a program on these by punching holes, but well, you had to bring them to the computing center, right? Your homework, right? And then wait few days later whether it run, right? Whether you didn't have a syntax error, meaning syntax error could be just a simple you missed a punch somewhere, right? Not fun, right? You have a really long feedback loop, right? It's much easier these days when you have interpreted language. You write something, you get an answer immediately. You know where you failed immediately. The feedback loops are important. So yeah, okay, but let's go. So yeah, so this 19th century is all about these punch, you know, how you call them, punch cards, I guess, right? So in fact, you can see the loom here, actually, right? This is actually you have actually these punch cards, and basically you could think of it as like a domain-specific computer, but not really a full Turing machine, obviously, right? But there is actually some conditional branching. You can actually you can program because you can enter the design, right? Very big advancement. Okay, so yeah, let's go to the first. Yeah, I'm skipping ahead, but she is considered the first programmer at the Lovelace. In Latvia and actually worldwide, we celebrate the Lovelace Day, the Programmers Day. Now the question was, which day was it? I think it is 256, day 256 or was it her birthday, or was it 256 day of the year? Who can look up what's the Programmers Day? I think it's day 256.
Yeah, 256.
Which is like
September
something, yeah. So that's the Programmers Day. But yeah, but at the Lovelace, she was daughter of Lord Byron, right? Very famous poet, right? But she was basically a mathematician, a logician, right? And also I would say she was basically, so she's first programmer. Do we see her first programs? I think we'll see, yeah. So this is like one of the first like world's actual real program, right? This is a Bernoulli number per calculator, right? I know I've shown you this before, right? These are actually kind of non-trivial program, actually, right? Not Fibonacci numbers, but normally numbers are slightly more difficult to calculate, right? So she wrote notes, and she was basically, I would say, Steve Jobs of the analytical engine. Meaning, well, I mean, she is actually a programmer, but she was more than Steve Jobs because she could actually write some programs. But what she did is she went around Europe and sort of like said, okay, here's this amazing machine, this analytical engine, right? It could do anything, right? You know, give us money or give us, you know, we can do just any problem. It's like today with ChatGPT, right? Anything we can do basically, right? And yeah, we can do a lot of things, right? But in those days, actually, well, the problem was they didn't really have fully operational machine, the difference engine, which analytical engine was sort of working, but the new hotness, the difference engine was not ready, was not built in Charles Babbage time. So unfortunately, Ada Lovelace, she had a pretty short life. She died around 40, right? So, but she lets her mark in this regard by writing these programs and also by popularizing this idea of this machine, right? So, very influential, right? So she wrote an algorithm basically, and again, so this idea of general computing, basically, we don't have a machine for specific, like the loom is specific for weaving patterns. We have this domain, general domain, independent from many domains language, right? So, and she made actually, you could say, so Babbage was more into the math, right? But Lovelace would say, okay, yeah, this is going to be great. I mean, one day, we can do anything basically, music, art, you name it, right? So, I don't know. She mentioned gaming. I don't know, right? But yeah, so there's loops inside, right? There's iteration, right? There's actually some error checking, right? Of course, right? So, big inspiration, right? But now, of course, I'll skip to the 20th century, and of course, we'll get to Alan Turing, right? So, obviously, one of the founding figures, right? And we get the Turing machine, and again, this is important for our programming language because, of course, the programming language we'll be talking into today's course, and most programming languages are so-called Turing complete languages, meaning, well, they're all basically can do the same thing. So he came up with this Turing machine, right? So what's Turing machine look like? What is the idea? I can show you here. There's one. So what does it have?
It's like it reads a state and then it can switch states and break and from an infinite, I think infinite. Like
it has So or Turing basically. So technically, we don't really have a Turing machine, right? Because we don't have infinite tape, right? Mm-hmm. Technically, right? But the idea that he came up with this very simple machine. We have this infinite tape, assume infinite memory. As you know, the mathematicians in general like to make these assumptions. Assume infinite anything, right? So yeah, we have this infinite tape, right? But using this, right, you can simulate basically logic of any normal computer algorithm, right? Given enough time and resources, right? So you have this head, right? Can move left or right across the tape. There's symbols, right? So there's only a couple of rules, right? I think basically what it has to include, what's crucial, you need to have a conditional jump, basically, right? You have to make a choice. Yeah. Basically, if statement. If there's an if statement with a jump, right? That is kind of like the thing which makes it work, right? If you don't have this conditional jump, you don't really have a Turing machine, right? You need some sort of there's many ways of doing this conditional jump, right? But if you don't have this construction, right, then your language is not Turing complete. So that leads to like why HTML is not Turing language, right? But CSS, funnily enough, is, right? You could use CSS to write an emulator for, let's say, C++ or Python, technically, right? I don't think anybody has done it yet, right? But that would be a really scary exercise, right? But yeah, so this leads to the fact that most languages, right, underneath, they can do this. They have the same power, right? So Pascal, C++, Python, Rust, Go, you name it. They're all equivalent, right? Basic, right? You will not assembly, right? But you probably would not want to use some language for other things, right? But the difference lies within, of course, or human, human content of this language. They're equally powerful, right? But of course, some languages are more fun to write, and some languages are more fun to read, right? At least not painful to read, right? So again, the language BrainF, right? The full name I'm not going to say here in class, right? It's very close to Turing machine, basically, like as he envisioned, right? So yeah, you can make your own language using this, his approach. So it's very significant, right? So universal, right? Because what you can do is you can make emulator for emulator, so emulators for another emulator and so on, right? So that's like you have seen this. Sometimes you see people on YouTube like they wrote like some game inside Minecraft, or like some Super Mario World somewhere has some emulator somewhere, right? You can emulator can emulate an emulator, and so on and so on and so on, basically, right? So that's a very foundational idea, right? So now, again, and of course, so this leads to the foundation to the high-level languages, right? And of course, again, underneath, right? This is sort of like the hardware also. You have it sort of works, most of the computer hardware basically kind of like works like Turing machine, except of course we don't have infinite tape, right? So again, remember, he wrote this in 1930s. He didn't have a computer, right? He just wrote this theoretical idea, right? He got to work with some computers in 1940s early, right? They were not really general. ENIAC was not really general, right? But when breaking the Enigma, the German code, right? So, and of course, when we talk about AI, of course, that's a different story, impact on artificial intelligence. But let's not talk about that right now here. But this leads to another guy, Alonzo Church, right? And if there's a movie about Turing, I don't think there's any movie on Alonzo Church. But he was actually sort of like, at least as is influential on the computer as far as programming languages, right? This guy here, right? He was a logician, right? So he had a different approach, right? Again, in those days, you don't have a computer science, right, department, right? You had basically mathematicians doing most of the work, right? So theoretical calculation. So he came up with his own calculus, right? Of course, when we say calculus, right, not Leibniz calculus like what we learn in school, right? But actually a way of computing, basically, right? So his idea was for functions, right? So basically everything is a function. You sort of make an abstract function, and you can use that to sort of do anything. Or could you do everything? Well, what do you think? Was his idea as good as Turing's? Why not, right? So, well, it turns out, yeah, they came up, well, the Church-Turing thesis, right? 1930s, again, no computers yet, right? Basically, Turing machine, what can Turing machine can do, right? Church lambda calculus can do too, and back forth. Right? So they're equivalent, basically, right? And this is important because why? Because some of the language we'll learn in this class, right? Like Lisp-based languages, like Clojure, right? The functional languages, right? They're just as powerful as the regular imperative language, you know, like classical Go or, you know, or BASIC or, you know, or so on, right? So there's two different ways of formal ways of defining a programming language, right? But they're equivalent, right? So very significant, this Church-Turing thesis, right? So there's unified framework, right? So, and also, of course, it led to also, again, as far as CS goes, there's some, whether there's some problems can be solved in general. There's some limits, of course, right? So, language like Lisp, Haskell, Scheme, other languages, right, have very been influenced by this church approach as well, right? So, leads to functional programming, right? So, again, if you're interested, you can read, if you read the philosophical part, Plato at Stanford Education has a pretty good overview of what he came up with, right? But luckily for you guys, we're not going to go really heavily into church in a lambda calculus, right? So now we actually get to first programming language as we understand, and it's done by Konrad Zuse. Zuse, yeah, right. And he came up with Plan Calcul, right? And it's kind of, I would say, not a sad, well, it's kind of sad story because he developed his programming language in between 1942 and 1945, right? So that was the time, right? It was not published or implemented years later, right? So you know, world had other problems at the time, right? So he was in Germany, right? He was actually, I guess, from what I understand, he did not have a German, you know, Nazi, you know, government funding, right? He didn't actually, I guess he was not a good seller, right? You know, he did not try to convince anybody of, you know, how this invention would be good, right? So what's interesting is, right, that what kind of computer was this built on? What kind of computer was this language meant for? Anyone know, what was it, electronic? No, right. It is basically built in between 38 and 39. So this was not electronic, it was electromechanical computer, right? Let me show you a picture of it. Electromechanical computer. Yeah, Z3. Looks like, well, again, it's a replica, of course, right? Let me go give you a link, not like this big, let's go small picture. Yeah, Z3. So it was basically, his idea was, remember Charles Babbage, right? He used just mechanics, right? But by 1930s, we have a relatively cheap electricity, and we have these electromechanical switches used in phone switching, right? Phone companies, right? So didn't have anything much else, right? So very interesting approach. What do you need switches for in a computer, right? You need to store data, right? You can use it to store zeros and ones in switch, and also, of course, making conditional jumps, right? Switches are used, right? So Z3. Oh yeah, let's see. Oh yeah, there you go. Okay. So this is a computer, basically, right? He wanted to use for this, right? So first fully functional programmable electromechanical digital computer, right? So this is a few years before digital computers. So again, difference is you don't store the data, it's stored in these switches, basically, right? You don't have in modern computer you have switches too, right? Except they are much, much smaller, right? A couple billion times smaller, right? But and they are electronic, right? This is actually just switch based. So how fast was this computer? I think it was. It was not thousand. I think it's like 1 hertz. It's like 1 operation second, basically, I believe, right? But yeah, but this language was going back because this course about programming language. The idea was, well, he came up with basically a lot of modern ideas, right? Simple data types. He had floating point integers, right? Things he.
How I remember, actually, Enigma was also like electromechanical
Yes.
computer, and it was introduced earlier.
But yeah. But the thing is, okay, you're right completely. But Enigma is very specific. It's domain specific, right? It's a sort of thing. It does something, right? It's not. You cannot make a cooking recipe using Enigma, right? I mean, to calculate your ingredients for cooking, something, right? So that's the difference. You can make all kinds of so Enigma is closer to the loom, right? The loom from 19th century, right? Because it does something specific, right? You don't have I don't think Enigma machine itself is Turing complete. I might be wrong. Maybe somebody came up with some idea how you could sort of you can't install Linux on Enigma, right? But theoretically.
Turing algorithm, but very rudimental one.
Yeah. So yeah, so that's the question. Yeah, if you can somehow squeeze in the memory storage into Enigma and you have looping or branching, maybe you could. This would be an interesting topic, by the way. Again, for the optional report, if you can show how Enigma can actually be used as a general purpose computer, it would be great. So that's the thing, right? Some things later on only you can find, okay, yeah, if you add a couple things on, yeah, we could make this general purpose computer. Why would you want to do it? That's another question, but yeah, it's like people who write Tetris in Excel, right? Same thing, basically, right? You can do it, yeah? And, all kinds of fun stuff you can do, right? Yeah, to me?
I said you speak about Tetris on Excel. I said about Doom 1 on Freezer.
Oh yeah, you can do. That's another thing. Can it run Doom, right? Can it run Doom, right? Reddit, there's one.
Yeah.
It'll run Doom.
It's a cool.
Yeah.
Cool.
It runs Doom, right? So I checked every few months see what news device they have, right? So there's some really cool, yeah. Oh, that's pretty cool. This what is this? Like a monitoring device? What is this? This looks like a heart.
Yeah, heartbeat device.
Yeah, that's awesome, right? Yeah, yeah. You can run on a fridge or whatever, right? Yeah. So that's same idea. Yeah, you can adapt things. So I believe the Enigma thing is you could do something, but I think the problem is with memory, right? And again, Yeah, how much memory had. But yeah, so going back to Planck, cool, because this is really a first real programming language, because it has simple data types, it has arrays. I mean, right? Records. So what's records? Like structure or class, well, structure in C or C++, right? Boolean algebra, right? He also, there was sort of pseudocode as well, right? So basically very, very powerful and great thing, but was it actually influential? Not really, because it is sort of like a side quest basically, because nobody really, the people who are doing research and doing the popular things, like who actually came up with programming language later on, they really didn't know about this language till much later, because again, it was during the World War II, right? And didn't publish too much, right? So it didn't really influence the early programming languages like Fortran and Lisp, right? So later on, yeah, it was significant. It was like sort of had many firsts for a programming language, but it didn't really sort of. It shows, I guess, it shows that independently many people have same ideas. I mean, it's just like you need floats, right? You need integers, right? Obviously, you need arrays. I mean, that might not be so obvious immediately, right? When I was starting to learn programming on a basic, I didn't realize you need arrays, how good arrays are, right? My first programs, right? Only then later on when you start writing multiple variables, A1, A2, A3, A4, A5, you realize well, you need an array, right? So same thing, right? Records, structures. That's even less obvious. Why would those be, why would you want to use those at first, right? Well, you don't have to, but they're actually quite nice if you have something like this, right? Structures, right? Maybe your own custom data types, basically. Grouping data fields together, right? So, okay. So, before the break, so again, before 1950s, before the actual people who came up with the first early real digital computers, well, we use the 0 and 1 technique, right? You use switches to program, right? Extremely laborious, right? So you physically manipulate the switches, basically, again, Turing's machine, right? So very, very hard. You have plug boards, right? You plug things in, right? And wires, right? So programming is physical programming, right? So you put things together, basically. I would let's see if we get a picture of this, right? So, do I have a picture of it? No, I have the machine. Yeah, you can see it a little bit here, right? This is ENIAC, right? So, electronic numerical integrated and computer, right? Right, so of course they used for what? They use it for military use, artillery trajectory calculations, right? So programming was, extremely laborious task, right? You need to connect two data points together, and you actually had wire, right? So, so basically, if you need to change the logic of your program, you actually had to adjust the wiring, basically, right? So, this is, very hard. Basically, you could make custom calculations with this, right? Because it's programmable, right? So I would say it's kind of like, I'll make an analogy with the analog music synthesizers these days. Like you also do wiring, right? You can make your own sounds using wiring, right? Anybody has played around these days, synthesizers, right? That's something like that, basically, right? So also, there was no real programmer as such, right? So you had these interdisciplinary teams. You had to have a physicist, engineer, a mathematician, like figure out how to write this together, right? And of course, debugging, right? Debugging was extremely hard, right? And plus, of course, you had what is another challenge with these machines, right? These run on what? On vacuum tubes. So a big problem was
changing the tubes.
Yeah, I think I mentioned this before. Like, if you have 8,000 tubes, right? On average, like one will fail every hour or so, right? So you store every 2 hours, right? So because they burn out, right? So, so you do something and then you change tubes, run something else for a couple hours, and not fun. Well, but it was, again, there was a big driving need, right? Military use, of course, right? So very physical labor. Maybe let me see if I can find a picture of Early programming switchboard, 1940. No. No, that's not telephone. That's, you see, it's similar, right? Computer, early. Let's see if we can find a picture before the break. Yeah, Konrad Zuse, we already talked about him. Yeah, this is like 50, this looks like 50s to me because I see some spinning tape. Well, yeah, this is more like, all right, something like this is more like it, right? Yeah, so this is history, right? So that's what programming was like, right? pretty interesting, right? So, well, interesting, but I would not want to do this, right? Let me show you here. Oh, that's a Google, that's proxy. Why did I? Okay, let me see. I guess history. It's History Channel. That's kind of not a good source because they are liable to. Let's do this one here. This is I rather. Yeah. I don't trust this data source. On Alt early computer programming or G. All right. Now. Okay. So we'll hopefully know by now. Okay, and I guess we can end this part here by the first bug, and it was a real bug, right? Very story, right? Of course, some say it's not really bug, right? But yeah, Grace Hopper, right? Turing Award winner, right? Famous lady, one of the pioneers, right? That's the story goes, and apparently this is actually it is attributed, right? Not completely a legend, right? Right? Relay. There's a MOS in the relay switch, right? Again, we call them electronic computers, but they still use switches, right? Memory was the vacuum tube, but still some of the logic was actually using switches. But yeah, so you could say this is the actual bug, first real bug, right? Again, maybe not the same usage of how we use bugs today, right? This is like a hardware fail, right? Basically, right? But the question is, was this actually why bugs? We call them bugs, but you know, American history, that's they say, yeah, the actual real physical bug. Okay, let's take a break for about 30 minutes. We'll start at 12:10. Yeah, 12:10, and we'll continue what happened afterwards. Any questions? No. Okay.